So the input sequence is already sorted. What is going to happen to the complexity of insertion sort? Yeah, I need an explanation. I mean, I need the value of the complexity and why. Because? Yeah, true, exactly. If it is, if the sequence is small, sorry, if the sequence is in increasing order, okay, and we are trying to sort in increasing order, like this algorithm is implementing, then this condition will never be true. It's increasing order, so all the values to the left are going to be smaller. So this value, this condition will always be false. So this loop will never execute. In other words, it's going to be big of 1. So, and this is big of n, and this is all that stuff here is big of 1. So it's a bunch of big of 1s inside the big of n, and hence the complexity is going to be big of n. Now, selection sort, if we give selection sort a sorted sequence, what's going to happen? What's the complexity if it's a sorted sequence? We have seen that if we give a sorted sequence to insertion sort, the complexity will be big of n. And we call this the best case. So the best case complexity of insertion sort is big of n. And it happens when the sequence is already sorted. Now, can we say the same thing with selection sort? When the input to selection sort is a sequence which is already sorted, what is the asymptotic complexity? Huh? I mean, if you remember what we have seen, what we have said about selection sort, what we are going to do, we are going to start from the first element, and we are going to try and find the elements to the left, find the smallest one in the left, and compare it with the current element. So again, just think of applying the same algorithm. Let's say the initial sequence is sorted 1, 2, 3, 4, and 5. Okay, so and we are going to use selection sort. So we are going to look at the first element. Okay, so it's 1, and then we say it's the smallest one, and we are going to look if there is a smaller element to the right of 1. So we are going to visit that, and visit that, and then we conclude there is no smaller element, and indeed 1 is the smallest one, so it stays where it is, and we don't do any swapping. And then we move, so it stays like it is, and then we move to 2, and then we say it's the smallest, but then we compare to all these. Maybe there is a smaller one, but there is no smaller one, because 2 is the smallest, since this is an ordered sequence already. So as you can see, if the input is ordered, it is not going to help selection sort. We are always going to look at the elements to the right, because we need to check if there is a smaller element. So if the sequence is sorted, selection sort will still have the same complexity, big O of n squared. However, insertion sort will not, because of the condition inside the while loop. And it's quite clear from the code of selection sort is that this loop is a for loop from 1 to n, and this loop here is also a for loop from I to n. So they are going to execute anyway. It's not like the while loop where it does not execute if one of the conditions is false. So this is different. Okay? So this is saying, so this here we are talking about the complexity of selection sort, of insertion sort. Yes, complexity of insertion sort. And then the average case of selection and insertion sort is that. The best case is that insertion sort is linear when the input sequence is sorted. And the reason is quite simple, because in selection sort we are always going to visit all the elements to the right, whether they are sorted or not. But in insertion sort we are not going to do that, because we are going to stop as soon as we find an element which is smaller than the current one, and that's why it's different. Now, do you have any questions so far? No? So now we move to another sorting algorithm, which is a simple one. So now we move to another sorting algorithm, which is a simple one. It's called merge sort. Okay, merge sort is based on an algorithmic technique that we call divide and conquer. Now, divide and conquer is something very simple. It's an algorithmic technique. Okay, it is not exclusively used for merge sort. Okay, so merge sort is not the only algorithm that uses divide and conquer. Divide and conquer is a general algorithmic technique, and it is applied to merge sort. Now, what it means, sometimes we have a problem that we need to solve. That's the problem we need to solve. But it is very hard to solve. So what we do is we divide it into, let's say, two different problems, P1 and P2. Okay? So the problem, we divide it into P1 and P2 so that we can solve P1 and solve P2 and then combine the solution in order to get P. Obviously, not all the problems in the world can be divided using divide and conquer. Sometimes a problem you cannot apply divide and conquer to it. However, for sorting, we can apply divide and conquer. So this is a general description of what is divide and conquer. We have a problem P, and then we cannot solve it. It's hard. So we split it into two smaller problems, P1 and P2, such that solving P1 and solving P2 separately, then we will enable us to solve problem P again by combining the solutions. Now, say that P1 is still hard to solve. So P was hard, we divided it into P1 and P2. However, they are still hard to solve. So we divide them into even smaller problems, P11, P12, P21, and P22. And we try to solve these small problems now. Now, If we can solve P21 and P22, we combine their solutions to solve P2, and then solve P11 and P12, and combine their solutions to solve P1. Now we have a solution for P1, a solution for P2, so we combine these two solutions in order to solve problem P. This is divide and conquer. So dividing the problem and then conquering the problem. Basically, it's like a big country you want to colonize, and you cannot just go and fight everybody. So what you do is you separate these people into different groups. So you go and tell this group that this group here over here, they hate you, and this P1 hate you, so they are separate. And you go and conquer this group, and you go and conquer this group, and then by conquering that and conquering that, you have already conquered the country that you want. So this is divide and conquer. You go and conquer this group, and then by conquering that and conquering that, you have already conquered the country that you want. So this is divide and conquer. It's an algorithmic technique when you have a problem that you cannot solve, and actually you can apply divide and conquer to it. You can divide it into little parts and divide them recursively until you reach small enough parts that you can solve, and then you combine the solution to these parts recursively until you find a solution to the largest original problem. This is divide and conquer for algorithms, and we are going to see how we are going to apply it in the problem of sorting. Okay. So the idea is we are going to split so the sequence is like our problem. We have to sort the big sequence. We are going to split it into smaller parts and try to sort them, and then split them, and then split and split until we are able to sort them, and then we combine, and we will see how this works. So that's the general idea. Okay, so by analogy, before we forget what's divide and conquer, that divide and conquer by analogy in terms of sorting, we have a big sequence S. We want to sort. We cannot, or we are lazy. We say it's too big. So we divide it into smaller sequences, S1 and S2. Try to sort them. Still we can't. Divide them into smaller sequences, S11, S12, S21, S22, and continue doing that. Once we have small enough sequences, we will see what it means to have small enough sequences. Once we have small enough sequences, we can sort them, and then we combine them again together in order to find the sorted version of S, which is S prime. Okay, that's the abstract description. Now we're going to see an example of how things work. So I hope this table is not too dense. So again, this is our initial sequence. Okay, that's our initial sequence that we are going to sort. So we said we are going to use a divide and conquer algorithmic technique, and we call this merge sort. Why merge? Because of the merging step that we are going to see. So this is our initial sequence. So we said we are going to divide it into smaller parts. In our case, smaller parts are going to be two parts of almost equal size. This is not a requirement in the general case for divide and conquer algorithms. You can have a divide and conquer algorithm that splits the problem into 3 parts or 4 parts. As long as you're splitting to make the divide and conquer algorithm that splits the problem into 3 parts or 4 parts. As long as you're splitting to make the problem easier, you are dividing. Okay? In merge sort, we are going to make a division by 2, but obviously sometimes the sequence is not an even number, or the size of the sequence is not an even number. So we cannot say we are going to divide the sequence into two equal sized subsequences. So we are going to say we divide the sequence into almost equal sized subsequences, because the sequence can have an odd size like 11. How are we going to split 11? I mean, 6 and 5 is okay. 5 and 6 is okay. Okay, so this is our original sequence here. So there is a partitioning part here. There is partitioning number 1. We are going to divide the sequence into two parts here, like that. Do you see the two parts here and here? Right. Now, and then we are going to say, now, can we sort these? And then we say, no, we cannot sort them yet. And then we are going to divide the sequences again. Because they are odd numbers, we cannot get equal size subsequences. So we end up having 9, 4, 8, 7, 1, and then 6, 2, 10, and 5, 3. And this is the next partitioning level. This division is called partitioning. Okay? And then we say, no, we still cannot sort these guys, so we are going to split even further. So this one is split here, this one is split here, this one is split here, and this one is split here. And then that's what we get. Can we sort these? No, still we cannot. So we still have to split sequences like that. And at the end, the very last partitioning level, what we get subsequences of size. Which size are the last subsequences? 1, exactly. Now, once we find these ones, once we find these subsequences, now we are going to merge them. Obviously, merging them is going to require some work. So, during partitioning, we have been lazy. We have been just dividing, and each time saying, no, I still cannot do any sorting, no, I still cannot do any sorting, until I reach sequences of size 1, and then I say, okay, now I can start doing some sorting. Now, what it means to start doing some sorting, we call this the merging step. So, what we are going to do, we are going to work backwards. Okay? I mean, if you see here, we are going to start with 9 and 4 because they belong to the same sequence, to the same subsequence 9, 4. We are going to put them in order. Okay? 4, 9. So 9 and 4, we are not just going to merge them, because if we just merge them, we are going to get this sequence again, which is not useful. We are going to compare them and put them in order. So we put them and they become 4, 9. 8 is alone, it stays like 8. 7 and 1, we are going to merge them by comparing them, and they give us 1 and 7. And then 6, 2, they give us 1 and 7. And then 6, 2, they give us 2, 6. 10 stays the same. 5 and 3, we are going to merge them to become 3, 5. Now we are going again to merge these guys. Okay, 4, 9, 8, because they belong to the same sequence here. Okay, so we are going to order them. We will see how do we order them, but right now we want to understand the general shape of the algorithm. So we have now sequence 4, 9 and sequence which contains 8 only. We are going to merge them. While merging them, we are going to sort them as well. So 4, 8, 9, sorted. 1, 7, okay, stays the same. 2, 6, 8, we sort it. 3, 5, stays the same. And then we are going to merge this and this, and they give us 1, 4, 7, 8, 9, and merge this and this, and they gave us 2, 3, 5, 6, 10, and finally merge this and merge this, and we get the original sequence, but in sorted fashion. Okay. Now, if you look carefully, this is the original sequence, and this is the sorted sequence. This is the original sequence split into two subsequences which are not sorted. This is the original sequence split into two subsequences which are sorted. Okay, there's a lot of noise. Please calm down. If if you feel okay, can you please calm down, or just leave the class? I will not mark you as absent. I will make a particular exception today and every day. Okay, please, no speaking in class. So this is the original sequence, and this is the same sequence sorted. This is the two halves of the sequence, and they are here sorted. And 3 5 5 3 is sorted. So for every partitioning step, there is an equivalent. There is a corresponding merging step. For each partitioning step, there is a corresponding merging step. Okay, so that's how merge sort works. So dividing or partitioning is easy. There's nothing big. There's no big deal about it. We are just dividing into smaller parts. Now the merging is where we are going to do something useful. So how does the merging work? Let me see the merging if I have an example. Yeah. So here I am considering the merging of. Obviously, there are lots of mergings here happening, right? There is this merge. There is the merging of 4, 9, and 8. The merging of 2, 6, and 10. The merging of these two together. The merging of these two together, and then the merging of these, and then the merging of. There are lots of mergings. What I am going to explain in the example is the largest merging, which is the merging of these two together, and then the merging of these, and then the merging of. There are lots of mergings. What I am going to explain in the example is the largest merging, which is, which is this one. This is what I'm going to explain in the example. So how do we do the merging? Okay, one thing, one important property about merging is the following. Because these sequences are of size 1, each one of them is sorted. Okay. A sequence which has size 1 is sorted already because it has one element. When we merge them, the merging operation ensures, or the output of the merging operation is that this sequence is sorted already. It is sorted by the end of the merging. That means that each time the input to the merging operation is 2 sorted sequences. Okay, so the input to this merging operation is 9 and 4. Both are sorted, and the merging operation gives us a sorted sequence. And then the input to this merging is 4, 9, which is sorted, and 8, which is sorted. And then the input to this merging operation is 4, 8, 9, which is sorted, and 1, 7, which is sorted. So each time the merging is using the result of another merging operation, and because all merging operations give us sorted sequences, so the input to a merging operation is always sorted. So that's an important property which is going to help us in terms of complexity. So this is the last merging operation. The array has 2 parts: 1, 4, 7, 8, 9, and 2, 3, 5, 6, 10. And we are going to merge them. I'm using an array called result. This result is going to contain the result of merging A1 and A2. Are you following me? Right. So from here on, it's pretty simple. So what we do is we are going to compare the first 2 elements of the 2 subsequences. Okay? So we are going to compare 1 and 2 here. We are going to compare 1 and 2. We find that 1 is the smallest, so we remove it and put it in result. Okay? So we compare the first element of A1 with the first element of A2, and we remove the smallest of them and put it in result. So the result of that is that now result contains the element 1, and A1 has lost the element 1. And again, we continue doing that. We compare the first element of A1 and A2, and in this time it's 2 which is smallest, so we move it to result, and 2 loses the element A2 loses the element 2. And we continue doing that. Each time we are comparing the first element and putting it in result. Okay? Now, at the end, we keep doing that. At the end, result is going to contain the sorted sequence. Okay? So at the end, we remove everything.